Now, in continuation with the introductory lecture of wave equation, in this second lecture, we are going to discuss or study the actual formulation of Schrodinger's wave equation. In introductory part, we have already discussed what is Schrodinger's wave equation. Means it is a kind of a differential wave equation in psi where an operator acts on the wave function and which will produce the future behavior or the evolution of the wave function in time and space. Also, we have seen that the wave function will be in two forms. The first form of the wave function is Schrodinger's time independent wave equation, and the second form is Schrodinger's time dependent wave equation. Now in this lecture, we will discuss or we will set up both the forms of Schrodinger's wave equation. Now let us formulate the first part, which is Schrodinger's time independent wave equation. Now to formulate Schrodinger's time independent wave equation, we have to start with the de Broglie's hypothesis of matter wave. And according to de Broglie's hypothesis, as every moving object is always associated with a wave known as matter wave, and the motion of the particle will be guided by this matter wave. And the wavelength of this matter wave will be given by lambda equal to h by p, where h is known as Planck's constant and p is known as the momentum of moving object or moving particle. Here this lambda is equal to h by mv. But to formulate Schrodinger's time independent wave equation, as this is a wave equation, therefore we must know the general wave equations which will be applicable to any kind of wave. If we want to study the motion or the dynamics of a wave, then the simplest kind of second order differential equation will help us to understand the wave motion. And that second order differential equation will be related with the time coordinate and the space coordinate. For example, for the given wave function psi, the general wave equation can be expressed as the second order time derivative of psi is related with the second order space derivative of psi in connection with the velocity of the wave or the square of the velocity of the wave. So therefore the form of the general wave equation is like that: dabba 2 by dabba t square of psi will be equal to v square into dabba 2 by dabba x square of psi plus dabba 2 by dabba y square of psi plus dabba 2 by dabba z square of psi. Or the same can also be expressed as dabba 2 by dabba t square of psi will be equal to v square into del square psi. Here dabba 2 by dabba t square as well as del square are acting as an operator, whereas psi acts as an operand, or it is known as wave function. The del square is known as Laplace operator and its form is dabba 2 by dabba x square plus dabba 2 by dabba y square plus dabba 2 by dabba z square. Now to set up Schrodinger's time independent wave equation, we have to start with suitable wave function. A wave function means a function of space and time coordinate, that is psi. So therefore let us select psi is a kind of pure mathematical exponential function, that is psi of x, y, z, t will be equal to psi 0 of x comma y comma z into e to the power minus I omega t. Here psi 0 of x comma y comma z represents the amplitude of this wave function psi. We can simply represent this wave function as psi is equal to psi 0 times e to the power minus I omega t, where psi 0 is the amplitude of the wave function and the basic wave function is a kind of exponentially decaying function of omega and t. As wave function is a kind of second order differentiation of time variable, so therefore we have to differentiate this wave function psi with respect to time. And remember here the differentiations are partial differentiation. So therefore dabba by dabba t of psi will be equal to psi 0 will be as it is, and also the derivative of exponential function is exponential function as it is times the derivative of minus I omega t, which is minus I omega. So therefore the first order derivative of psi with respect to t is dabba by dabba t of psi will be equal to psi 0 e to the power minus I omega t times minus I omega. So the effect of first order differentiation with respect to time is the multiplication of minus I omega term to the psi. If we again differentiate with respect to t, then we get dabba 2 by dabba t square operating on psi will be equal to psi 0 times e to the power minus omega t times one more times multiplication of I omega in addition to the first multiplying factor of minus I omega. So therefore we get the term of minus I omega times square. So therefore dabba 2 by dabba t square of psi becomes minus omega square psi 0 times e to the power minus I omega t, because the square of minus I omega term becomes, when we square the negative sign it becomes positive, when we take the square of omega it becomes omega square, but the square of I, which is imaginary unit, becomes minus 1. So therefore upon simplification, as we know that psi 0 times e to the power minus I omega t is actually the psi wave function, so therefore this will reduce to the form which is dabba 2 by dabba t square of psi will be equal to minus omega square psi. Give the number to this equation. This is the equation number 5. Now from this equation 5, if we substitute the value of dabba 2 by dabba t square psi in the general wave equation, which is dabba 2 by dabba t square of psi will be equal to v square del square psi. So therefore this v square del square psi becomes minus omega square psi. If we take this v square to the right side, then this becomes del square of psi will be equal to minus omega square divided by v square of psi. And if we take this term to the LHS, then this second order differential equation becomes del square of psi plus omega square divided by v square into psi will be equal to 0. Now if we substitute the value of this omega and the v in the term omega square and v square, then we know that the velocity of a wave can be expressed as the product of frequency and the wavelength. So therefore v can be expressed as nu lambda. Also the angular frequency omega can be expressed as 2 pi times nu. If we substitute the value of this v as nu lambda and the omega as 2 pi nu in the second order differential equation, so therefore this equation becomes del square psi plus, now in place of omega substitute 2 pi nu, so therefore it becomes 2 pi nu bracket square divided by, in place of v substitute nu lambda, so therefore v square becomes nu lambda bracket square times psi will be equal to 0. So therefore del square psi plus 4 pi square nu square divided by nu square plus lambda square into psi will be equal to 0. Now in this equation you can cancel out the term nu square. So therefore the equation becomes del square psi plus 4 pi square divided by lambda square into psi will be equal to 0. Let us substitute the value of lambda from de Broglie's hypothesis, which is lambda is equal to h by mv. Now in place of lambda, if you substitute lambda as h by mv, this differential equation becomes del square of psi plus 4 pi square divided by h by mv bracket square into psi will be equal to 0. So therefore del square of psi plus 4 pi square into m square v square divided by h square into psi will be equal to 0. Now try to replace this m square v square, means the momentum square, in terms of the energy of moving particle. The total energy of the particle can be considered as the sum of its kinetic energy plus the potential energy. If we represent the potential energy by capital V and the kinetic energy can be expressed as half mv square, so therefore the total energy can be expressed as E will be equal to half mv square plus capital V. Now if we rearrange, then we get the term of m square v square as 2 times m into total energy minus the potential energy of the particle. So upon substituting the value of m square v square from the equation 7 into equation 6, so therefore this differential equation becomes del square psi plus 4 pi square into twice m times E minus V divided by h square into psi will be equal to 0. So therefore if we rearrange the same equation like del square psi plus twice m times E minus V divided by h square by 4 pi square, it means h by 2 pi bracket square times psi will be equal to 0. So therefore this can be rewritten as del square of psi plus twice m by h cross square into E minus V times psi will be equal to 0, as we have substituted for h by 2 pi as h cross, which is known as reduced Planck's constant. And now finally this equation 8, which is del square of psi plus twice m by h cross square into E minus V of psi will be equal to 0, is known as Schrodinger's time independent wave equations. Here del square is known as Laplace operator, whose form is dabba 2 by dabba x square plus dabba 2 by dabba y square plus dabba 2 by dabba z square, and h cross is known as reduced Planck's constant, which is h by 2 pi. So that is how we can set up or the formulate Schrodinger's time independent wave equation. As long as the potential energy V is independent on time, we can solve any problem of the systems of microscopic particle with the help of Schrodinger's wave equation. Now let us discuss the another form of Schrodinger's wave equation, which is known as Schrodinger's time dependent wave function. Now the starting point for Schrodinger's time dependent wave function is, you should start with Schrodinger's time independent wave equation, which is del square of psi plus twice m by h cross square into E by V times psi will be equal to 0. Now for this Schrodinger's time independent wave equation, we have to separate out the term of E and the term of V, means the term of total energy and the term of the potential energy. So therefore, if we split, means if we multiply the psi to the E as well as to the V, therefore this equation take the form which is there in the equation 2, that is del square of psi plus twice m by h cross square into E psi minus V psi will be equal to 0. If we take this term to the other side, then del square of psi becomes minus twice m divided by h cross square into E psi minus V psi. Now if we take the term of minus twice m by h cross square to the LHS, then this becomes minus h cross square by twice m into del square psi will be equal to E psi minus V psi. Let's take this V psi term to the LHS. So therefore, this equation becomes minus h cross square divided by twice m into del square psi plus V psi will be equal to E psi. Now to convert this Schrodinger's time independent wave equation of the form in equation 3 into time dependent form, we should replace this E psi term in terms of the energy operator form. Now to develop the energy operator form, let's recall the wave function psi that we have selected while formulating Schrodinger's time independent wave equation. So therefore the wave function, the same kind of wave function is psi of x comma y comma z comma t will be equal to psi 0 x comma z into e to the power minus I omega t, the beginning step. Now if we differentiate this psi, the simplest form of the psi is psi equal to psi 0 e to the power minus I omega t, which is equation 1. Now let us differentiate this equation 1 of psi with respect to t. Then it becomes dabba by dabba t of psi, which will be equal to minus I omega times psi 0 into e to the power minus I omega t. But we know that psi 0 into e to the power minus I omega t is actually the psi. So therefore the first order derivative of psi, which is dabba by dabba t of psi, will be equal to minus I omega times psi. Now from Planck's quantum theory, energy can be expressed as E equal to h nu, where h is known as Planck's constant and nu is known as the frequency. As we know that omega is 2 pi nu, so therefore nu can be expressed as omega by 2 pi, and E is rewritten as E will be equal to h into omega divided by 2 pi. But we know that h by 2 pi is known as reduced Planck's constant. So therefore E is equal to h cross omega, and hence omega can be expressed as E by h cross. So let's replace this omega as E by h cross. So therefore the first order derivative of psi becomes dabba by dabba t of psi will be equal to minus I times, now omega is replaced as E by h cross into psi. So now on RHS, keep E times psi as a term and transfer this minus I by h cross to the LHS. So therefore, you will get E psi equal to minus h cross by I into dabba by dabba t of psi. Now to this RHS, if you multiply and divide by I, the imaginary unit, then you will get E psi will be equal to minus I square into h cross divided by I into dabba by dabba t of psi. But as we know that I square is equal to minus 1 and the previous minus sign becomes plus. So therefore, it will be IH cross into dabba by dabba t of psi. So therefore, if we replace this E psi from equation 5 into the wave equation, the general form of Schrodinger's wave equation of from equation 3, then this second order differential equation becomes minus h cross square by twice m del square psi plus v psi will be equal to, now E psi is replaced as IH cross dabba by dabba t of psi. This is known as Schrodinger's time dependent wave equation. If the potential of the microscopic system is a function of time or it explicitly depends on time, then we have to use this Schrodinger's time dependent wave equations, which is, here again I am repeating, minus h cross square by twice m into del square psi plus v psi will be equal to IH cross dabba by dabba t of psi. Here this del square is again known as Laplace operator, whereas IH cross into dabba by dabba t is known as energy operator, V is known as potential energy, H cross is known as reduced Planck's constant, and m is the mass of moving particle. So with this, here we have to stop.